सर लाइव हो रहा है? जैसे ही लाइव होगा ना।
हाँ।
Hello and good afternoon to everyone, and welcome to the webinar series conducted by Parul Institute of Engineering and Technology Diploma Studies, Parul University. Today we have a webinar on chemical engineering and catalysis, and we have a very renowned expert, Dr. Arun Basrur from Sood Chemi India Private Limited. Sir has more than 32 years of experience in the industrial catalysis and has expertise in the development of catalysts from lab scale to commercial manufacture in the areas of petrochemicals, refinery, and specialty chemicals catalyst. Sir has also end-to-end experience encompassing catalyst synthesis, shaping, characterization, performance testing, and application, and in selection of industrial commercial catalysts. So we welcome you on behalf of Parul University. Welcome, sir.
Thank you, ma'am.
Yeah, so we can start with the session.
Okay. Very good afternoon to all participants on this webinar. The topic today is chemical engineering in catalysis. And in this talk, I'll try to give you an overview of how catalysis and chemical engineering are related or connected, and also try to highlight where all the principles of chemical engineering can be applied in the area of catalysis. Catalysts are materials which alter the rate of chemical reactions, desirably increase the rate of chemical reactions. They are vital to the global economy. Projections for 2020 are 22 billion US dollars worth of sales from chemical catalysts with a compounded annual growth rate of 4.1%. Catalysts are materials which are used in so many areas of life that they touch almost every walk of life. Yet they are little known to the layman. So that's why they are known as behind the scenes player. And a catalyst is described as the heart of the process because it is the most sensitive component of the process, and it affects both the upstream and downstream if anything goes wrong with the catalyst. This slide shows the diversity of application of catalysts, whether it is food, fabric or clothing, pollution control, fuels such as energy, medicines, plastics and polymers, transportation, paints, furnishing, packaging, communication, entertainment. Most chemicals used in all these areas are produced catalytically. They use some form of the catalyst or another. The reasons we use catalysts are that they facilitate efficient chemical transformations. So you get better productivity and better economy. When compared to thermal reactions, catalysts facilitate higher product selectivity. And they also operate at less severe reaction conditions, or in other words, at the same reaction conditions, you get much better performance in terms of product yields. So that's energy saving. Lastly, catalysts have enabled replacement of hazardous chemistry and hazardous catalytic materials with clean green materials. So where does the chemical engineering connection come in? So when a chemist whose basic education is chemistry comes out with a catalyst formulation, the focus is more on composition, achieving properties, and characterizing the material. It is important to characterize the material for two reasons. One is to be able to improve and make better catalysts, and secondly, when the catalyst is manufactured, one needs to have some means of quality control or quality assurance. So the characterization, which is a determination of all the properties, is useful for these two ends. When it comes to using this catalyst in the process, one needs a lot of inputs from chemical engineers. So that's industrial catalysis. When it comes to achieving properties, many a times, like for example, delta P or the pressure drop, a chemist won't have an idea of what should be the allowable pressure drop in a catalyst. So that comes in from the chemical engineer. Kinetics, reactor design and sizing, process optimization are all roles that a chemical engineer plays in catalysis. I'll highlight the role of a chemical engineer in three different ways or in three different areas. One is as a catalyst user. The second is as a catalyst process technology developer. And the third is the role of a chemical engineer in catalyst manufacture. So let's start with the first one, as a catalyst user. So the main role of a chemical engineer here is basically monitoring and operating a catalytic reactor, doing iterative fine-tuning where needed to get the best out of the catalyst. So you have what is known as a mode of operation. There are basically three modes: isothermal, cyclic, and isoconversional. And you have an operating window. The operating window is essentially the range of process parameters under which the catalyst will give its best performance. So this information is given by the process licensor. It is developed and given by the process licensor who licenses the catalytic process. When it comes to the mode of operation, the decision on whether it is isothermal, cyclic, or isoconversional depends on the rate of deactivation. If the deactivation is slow, then one goes for an isothermal mode of operation, where the temperature as a function of time on stream remains practically unchanged over the entire cycle length. However, if the catalyst deactivates rapidly or fast, then one needs to periodically regenerate the catalyst. One way of doing this is to have parallel reactors. So in this figure here, we've shown 4 parallel reactors. The one that says inline is the reactor which is currently in use in the process. Once the catalyst in the inline reactor deactivates, it is taken offline. All the hydrocarbon, etc., is removed from this, and then it is subjected to regeneration. So regeneration essentially involves putting in a small amount of air or oxygen to burn off carbonaceous deposits. And then after that, a reduction step if it is necessary. So once this is completed, the reactor goes to what is known as a standby mode, and it is ready for replacing the first reactor, which is inline. When the rate of deactivation is moderate, then one operates an operating philosophy, which is known as isoconversional. So in isoconversion, as the catalyst deactivates, conversion drops. So this is compensated by increasing the temperature to maintain the conversion. So from SOR to EOR, there is the temperature is increased in steps in order to maintain the conversion. At EOR, either the design conditions of the hardware are limiting, or there is a design limitation in the ability of the catalyst to give selective product selectivity, at which point the run is terminated or the cycle is terminated. Some other things that a user or an engineer who's going to operate or monitor a catalytic reactor should know is the effect of process parameters. These constitute space velocity, temperature, pressure, feed ratio if there's a co-feed, effect of diluents if there are diluents in the feed stream, and response to process upsets. How the catalyst gets affected by process upsets and how one would respond to that. Two other things that need to be known are safe operation. So the licensor normally gives what is known as the safe operating envelope. So the information that is provided is the lower explosion limit, the higher explosion limit, and the auto ignition temperature of the constituents of the reactor. Then the information is also given on what are the conditions which can get the reaction into a runaway mode, how to prevent that, how to respond to emergencies. In this role, the main role of a chemical engineer is to operate the catalytic reactor efficiently and get maximum productivity from the catalyst. One way of defining maximum productivity is the amount of the metric tons or kgs of products, either per gram or per kg of the catalyst. Try to maximize that. Smooth startup and shutdowns are also very important, because most of the time the reactor will be operating at steady operation, but startup and shutdown are something that are that come in intermittently or very rarely. They come in only at the start of the cycle and at the end of the cycle. So one has to be very meticulous and careful in startup and shutdown. Both these processes are non-steady state processes. And these are the times which can lead to either an incident, an accident, or damage to the catalyst. One more thing that needs to be known is the effect of poisons. What can poison the catalyst? What materials or compounds in the feed can poison the catalyst? Whether the poisoning is reversible or irreversible, and what one needs to do to prevent these poisons from getting onto the catalyst. The last part is mishandling of catalyst. A couple of examples of this is some catalysts are damaged by when they are exposed to moisture. So in certain processes, you have steam being added to the reactor. In such situations, one must be very careful to see that the temperature does not drop below the dew point. Otherwise, the catalyst gets soaked in moisture or water and gets damaged. Similarly, when one is discharging a catalyst, there is a high likelihood of the catalyst being pyrophoric because it will have reduced metal as well as carbon deposits on it. So one has to discharge it very carefully in order to prevent a mishap like fire. Lastly, the process licensor provides conservative boundaries. So there is always some opportunity for further optimization, but this should be taken up only after clearly and properly understanding the process and its limitations. Otherwise, it can end up damaging the catalyst. Once the catalyst has completed its cycle, it's also important to know how to dispose of the used catalyst. The most desirable way of doing this is regeneration. In regeneration, you burn off carbonaceous deposits which are there on the surface of the catalyst by a controlled oxidation. Sometimes it is also necessary to redisperse the active phase which could have undergone sintering in the reactor. Regeneration can be done for most catalysts, but there is a limitation. Every time you do a regeneration, you lose some performance. So when a time comes when the performance loss is not acceptable, that is the time you dump the catalyst and replace it with a fresh charge. When this is done, in many catalysts, there are valuable metals. So the spent catalyst is sent for metals recovery. So the metals are recovered and then they can be recycled, converted into solution and used for making another fresh charge of catalyst. Once the metals are recovered, whatever remains behind is normally a refractory material which finds application in ceramic industry as a raw material. So it goes to the ceramic industry. If it is not useful in the ceramic industry as a raw material, then the last option is a secured landfill. So you basically dig a hole and put it into the ground. But this has to be done in a notified area, and care has to be taken that the catalyst which goes into landfill does not contain leachable metals. Otherwise, it has to be put into a separate container before it can be put into a secured landfill. So that completes the role of a chemical engineer as a catalyst user. Coming to the role as a process technology developer. A typical process consists of three areas. One is an upstream section of the reactor. So this is a section where you prepare the feed, bring it to the conditions where it can be fed to the catalyst and the catalytic reaction can be started up. So it will consist of compressors, pumps, heaters, heat recovery or integration for energy savings. It will also contain adsorbents or traps to remove poisons, potential poisons. It may also contain a distillation section to remove those components which are not useful in the process, that is components in the feed. Then comes the catalytic reactor, where the actual reaction takes place. And finally, a downstream section, which mainly consists of distillation, where you recover the product, the useful product, desired product, and the byproducts, recycle unreacted feed back to the upstream section. This essentially has mostly heat exchangers and distillation columns, which facilitate the separation and product recovery. So a chemical engineer plays a huge role in all three sections, upstream, downstream, as well as the catalytic reactor. And the main role is process design, equipment sizing and selection, and process optimization. So this is a typical flow sheet or a process flow diagram for toluene hydrodealkylation. This R101 in this oval is basically the reactor. Everything to its left is the upstream section, and everything to its right is the downstream section. To reiterate, a chemical engineer plays a major role in all these three sections, but today our talk is limited only to the catalytic reactor. Because of it, we'll be focusing only on this. Getting into catalytic process development, there are basically two key stages. One is lab scale development and evaluation of the catalyst, and then scale up. So why is it that we need to do a lab scale evaluation and a scale up? At the lab scale evaluation, that is the stage when a chemist identifies a suitable composition of catalyst and its properties, understands the thermodynamics of the reaction, which tell one as to what is the appropriate temperature and other conditions such as pressure to operate at. Then there is a need to determine what is known as intrinsic kinetics. So in order to determine intrinsic kinetics, one has to crush the catalyst into very small particles to minimize the intraparticle diffusional resistances. And then you also have to operate at high superficial linear velocities to minimize film diffusion. And if needed, if the heat changes or heat of reaction is significant, then the catalyst bed is diluted with inerts so as to render the operation isothermal. Efforts are made to operate as close to plug flow conditions as possible. Once this is done, the data that is generated is termed as intrinsic kinetics. So this intrinsic kinetics is the kinetic data which is not influenced or very minimally influenced by mass and heat transfer resistances. Once you have this data, you need to go to the commercial. The commercial plant. Unfortunately, when you have to use the catalyst commercially, it is not possible to use catalysts as such small or such fine particles which are of the order of less than 0.5 millimeter in size. It will result in unmanageable pressure drop and unmanageable dissipation of heat of reaction or heat transfer within the reactor. So essentially, when you use the catalyst on a commercial scale, you have to use significantly larger catalyst particles. The moment you increase the particle size of the catalyst, one ends up with mass transfer and heat transfer limitations or resistances. These affect the performance of the catalyst and decrease the catalyst effectiveness factor. The heat of reaction also affects kinetics as well as product selectivity. So therefore, there is a need to determine performance of the catalyst in the form in which it will be used in the commercial reactor and also under adiabatic operating conditions. Once this is done, we have access to what is known as global kinetics. After that, the next step is effect of determining process parameters to determine the operating window, identify runaways. This is not done experimentally. The runaways are determined through simulation. Determine the safe operating envelope such as LEL, HEL, AIT. This is again not done experimentally in the reactor, but it is done using a bomb colorimeter. After that, once you have the larger catalyst particle, then a CFT to ensure that there is minimum channeling or negligible channeling is also desirable. Having done all this, you have an engineer has sufficient information now to design an appropriate catalytic reactor. So in designing a flow catalytic reactor, one is type of reactor, which I'll elaborate on in my next slide. Then you estimate the catalyst bed size, which you will get to know from the study of intrinsic kinetics and the global kinetics. The aspect ratio, that is the length to the diameter of the catalyst bed. If pressure drop is critical, then one decides on whether one has to go for an axial pattern, which will give you relatively higher pressure drop, or a radial flow pattern, which will give you relatively lower pressure drop. Then depending on the heat of reaction, one has to decide whether there is a necessity for heat addition or heat removal, which means whether one is going to operate in an adiabatic mode or in a mode in which you can facilitate heat removal or heat addition to the system. Finally, it is the metallurgy, safety in design, and corrosion allowances. And all this at affordable cost. Once this is done, you have a flow reactor, right? You have designed the flow reactor. Now, coming to different types of flow reactors. When you have mild to moderate heat changes in the reaction, one can afford to use a fixed bed adiabatic reactor. Here you have a fixed bed of catalyst where the particle dimensions could be about 1.2 mm plus. If the reaction is highly endothermic or exothermic, then one has to resort to a multitubular reactor in which the catalyst is packed in these tubes, and either a coolant or a thermic fluid is passed through the jacket in order to either provide heat or remove heat from the reactor. So once this is done, so this is done basically for highly endothermic or exothermic reactions. Another way of when we operate multitubular fixed bed reactors, you use graded catalysts. In graded catalysts, the composition of the active phase is varied along the length of the tube in order to get maximum utilization of the tube length. Another way of handling exothermicity is to go for a fluid bed reactor. Here, the design is more intricate because the catalyst is now in the form of microspheroids, which are micron size in diameter, typically about 70 to 80 micrometers in size. And you have, since the catalyst is in a fluidized state, you will have particle to particle contact as well as particle to wall contact, because of which the catalyst has to have high abrasion resistance. And a drawback of fluid bed reactor is that one can anticipate or expect some loss of selectivity due to backmixing. Coming to catalysts, reactions or catalysts which deactivate very rapidly, one has to go for continuous catalytic regeneration, which is done by mechanically conveying the catalyst through a reaction section and a regeneration section. If the catalyst this is amenable when the catalyst deactivates over a few minutes or in the order of a few hours. However, if the catalyst deactivates very rapidly, within seconds or milliseconds, then one has to resort to a riser regenerator where you pneumatically convey the catalyst between the riser and the regenerator, like it is done in fluidized catalytic cracking. Other reactors that I used are membrane reactors. These are very useful in overcoming thermodynamic limitations, such as reversibility or such as the extent of reaction due to reversibility. In a membrane reactor, at least one of the products is removed from the reaction zone so as to push the reaction into the forward direction. So this completes opportunities where a chemical engineer has for catalytic process design. Okay. Coming to the role of a chemical engineer in catalyst manufacture. In catalyst manufacture, you basically have 3 steps. One is synthesis, which is done at the lab scale, and then the same thing is called manufacture when you do it at the commercial scale. Next comes characterization. And the third is application. That's you actually test the performance of the catalyst in a reaction skid. Coming to the first part, synthesis. 2 important processes that take place in synthesis are precipitation and crystallization. The mechanisms by which both these operate are very similar. The only difference is the time scale. In precipitation, as can be seen here, the moment the 2 reactants come into contact, there is instantaneous formation of a solid. Whereas in crystallization, the process occurs over either minutes, hours, or sometimes even a scale of a few days. What is the objective? So the objective in synthesis is to obtain a desired crystal phase and purity, particle size and crystallite size, shape or morphology of the particles, surface area and porosity, and adequate yield during precipitation and crystallization. These are the objectives. So what are different chemical engineering principles which can help us attain these objectives? One is, in both these processes, kinetics and mass transfer play a big role in achieving these properties. So the study of kinetics and mass transfer is important. And when here in both the cases, you prepare either a solution, a slurry, or a gel. These can have widely different densities and viscosities. And sometimes they could be thixotropic or dilatant, which is non-Newtonian behavior. So there is an opportunity to study the rheology of fluids. Now, studying the rheology is important in designing mixing equipment. CFD also helps in this. So eventually, through this, one ends up designing either a batch reactor or a CSTR, in which you decide on what kind of an agitator one would use, what would be the vessel internals, such as feed point location, like if one wants to have bulk mixing or micro mixing, the necessity for baffles, which will decide, all these will basically decide how the local concentration within the vessel changes and how the degree or quality of mixing change. So that is essentially designing a batch reactor or a CSTR. In achieving these properties, process control, process parameters are very, very sensitive. Any change in pH, temperature, concentration, especially these three parameters, can affect these properties significantly. So it's important to have very good process control. This company called Mettler offers what is known as a focused beam reflectance measurement device, in which one can take a real-time video of a precipitation or crystallization process as it is taking place. So this gives you it just enables you to study the change in particle or crystallite size as well as the morphology, and it's a very useful thing for understanding how particles grow. Now, when it comes to catalyst manufacture, as we saw on a previous slide, it is important the catalysts have to be formed into significantly large particles. So to do this, the first step involves dry or wet mixing, in which one makes a pliable putty kind of material, which can be deformed easily. This involves a lot of mixing, both dry mixing and wet mixing. In dry mixing, you would be blending two solid powders, and in wet mixing, it would be a solid and a liquid. Gas solid and gas solid liquid are rare. So different kinds of mixers and blenders are used for this. This photograph is of that of an IRIC mixer. As you can see, there's a drum, there's a scraper, and there's an agitator, central agitator. And this device has provision to either rotate the agitator clockwise or anti-clockwise, and the drum also clockwise or anti-clockwise. At the same time, the angle of tilt of this drum can also be changed. Other kinds of blenders that are used are some of them, of course, ribbon blenders, and then mix millers. Mix millers are used, basically consist of rollers which are used to compact and compact the putty to bring about very good compaction, essentially, along with mixing. The objective of mixing is to have uniformity and consistency of composition, so that there is no heterogeneity in the different catalyst particles that you make. From a chemical engineering perspective, studying the rheology of both liquids and solids, that's powders, there's a device known as FT4, which is useful in studying the rheology of solid powders. Then again, design of mixing or blending equipment comes in. The type of agitators one would use, the type of blades, internal of the drum, degree of tilt, rotation of the drum, the RPM, etc. CFD studies of powders. And since we will be dealing with solids now, which could be either a wet cake or dry powder, conveying and handling of solids also is an opportunity where a chemical engineer can contribute. That brings us to forming. So in the previous step, you make a pliable putty which can be easily shaped, deformed and easily shaped. Now, why is it important to shape or form the catalyst? Now, this is important basically to manage pressure drop and heat transfer dissipation. Heat transfer as well as dissipation of heat of reaction. So this basically is a photograph of a steam reforming catalyst which is supplied by Clariant or even Sudchemy. So we are joint venture partners. As you can see, it has got an intricate design and considerable voidage. So the reason this has considerable voidage is because this reaction is highly endothermic and it is carried out in multitubular reactors where heat is provided by direct fired heaters. So you have a flame impinging on the catalyst tubes. So if this heat is not removed effectively by convective flow of the reactant through the tube as well as reaction, the endothermic heat of reaction that is taking place within the tube, then there is every possibility of the tube getting overheated and undergoing either deformation, or in the worst case, it might even melt and cause a puncture, causing an accident. So these are the two key reasons: managing pressure drop and heat transfer as well as heat dissipation, that is important for forming and shaping catalysts. Now, there are different techniques used for shaping catalysts. In extrusion, the compaction is brought about by shear forces. In spheronization, compaction is done through use of centrifugal force. In spray drying, you use atomization across an orifice using either a pressure nozzle or a rotary atomizer. In rotary atomizer, you again use centrifugal force. Tableting, in which you use pneumatic pressure. The objective is essentially getting a uniform size and shape, getting uniform density. It is important to have uniform size and shape because if there is a wide range in size, then the smaller particles can go and sit in the voids of the larger particles and create pressure drop. Density is important because once a commercial reactor is designed and built, then the catalyst is filled in terms of volume. So if the density is too high, then you would be loading too much material into the catalyst, which is a loss for the catalyst producer. When you compact the material and increase its density, you will be losing out on porosity, which can affect the performance of the catalyst. And vice versa. If you have less density, then you will be charging less amount of catalyst in the reactor, which might affect the overall life of the catalyst. Excuse me. Mechanical integrity and attrition resistance are also important for this. So no sharp edges, smooth surfaces are important to prevent attrition or to provide good attrition resistance. So where does chemical engineering come into this? Relating shape and size to pressure drop, telling a catalyst developer as to what would be the allowable pressure drop, doing a simulation to determine what would be the extremes of conditions, so one knows what kind of mechanical strength and even thermal strength the catalyst particle should have, designing forming equipment, optimizing the operating parameters of the forming or shaping equipment in order to meet these objectives, doing a packed bed CFD simulation to see whether to minimize channeling, and DEM is basically discrete element method or discrete element modeling, in which one can try to determine what could be the maximum possible combinations of shape, density, and porosity within a finite volume. So this is useful to catalyst manufacturers. Next, we move on to heat treatment. So we first made a pliable putty, gave it shape. Now this material, and once we have given it shape, it is still a soft material which can deform. So it has to be subjected to some kind of baking or heat treatment so that it becomes strong enough to give it mechanical strength. So this step is known as drying and calcination. So the objective here is essentially to convert that soft pliable material into a hard solid shape which has good mechanical and thermal resistance. So this is done. This happens due to localized sintering during calcination. So you have bonding of different particles, local bonding of different particles, which lead to agglomeration and bring about mechanical as well as thermal, impart both mechanical and thermal resistance to the particle. During heat treatment, one more thing that happens is you have formation of different crystal phases and crystal size. These are again important for realizing proper performance or catalytic activity of the from the catalyst. One more kind of heat treatment is thermal reduction. Supported metal catalysts are used as when supported metal catalysts are used, the metal is in reduced form. So this can be done by thermal reduction in the presence of hydrogen. So this is another kind of heat treatment in which a catalyst manufacturer converts a metal oxide catalyst into a active form, that's a reduced metal catalyst, passivates it, and then supplies it to the end user. So the end user can straight away get started with the reaction and save a lot of time. Another option is chemical reduction. If not thermal reduction, you can use reducing agents such as sodium borohydride or hydrogen and reduce the catalyst. So the kind of equipment that is used for calcination and drying are static box dryers or continuous equipment such as spray dryers, spin flash calciners or dryers, rotary calciners, band or belt dryers. So when you go from static to box, you increase productivity. Criteria that are important is a controlled rate of temperature rise, choice of heating medium, because sometimes you can have a direct fired heater, but in some cases the catalyst is sensitive to flue gas where you have to have indirect heating. Uniformity of temperature across the entire heated zone, duration for which the catalyst will see the desired temperature, especially when you're doing continuous belt calcination, and also safety aspects. What kind of issues can happen if heat treatment goes wrong? One can have redistribution or segregation of the active phase, which will affect the catalyst performance. If the catalyst is subjected to too high a temperature, there can be loss of surface area. One can have color variation. Sometimes the color variation may not affect performance, but then it may not be acceptable to the customer. If the calcination is not done at the proper or desired temperature, one can end up with undesired crystal phase formation, which can affect the performance of the catalyst. It can also affect mechanical and thermal properties. So as a chemical engineer can contribute to equipment and burner design, process control, heat transfer, ensuring that there is proper designing so that you ensure that there is uniformity of heated zone, improving productivity, that is translating a static process to a batch process, to a continuous process. Typically, most catalyst developers in the lab would use static equipment such as box dryers. But when one goes to commercial, it is useful to use a continuous process for reasons of higher productivity. So then one has to translate this process to this, from static to continuous. Thermal efficiency, the material of construction used, the metallurgy used, cost, and also safety. So these are areas where a chemical engineer can contribute. A catalyst basically consists of two components. One is a support, which provides a high surface area, porosity, thermal and mechanical resistance, and the active phase, which actually does the reaction. So it is necessary to distribute this active phase onto this support. So in order to do this, this can be done in various ways. So one technique is known as impregnation. If you use a minimum quantity of solution just to fill the pores of the support, it is known as incipient. If you use excess solution, it is known as soaking or dipping. When you use an excess solution, the challenge there is to reuse the leftover solution. Now the profile or the distribution of the active phase across the catalyst particle can be either uniform, eggshell, egg white, or egg yolk. So if there are no issues of film diffusion, one can afford to use a uniform distribution. Whereas if the reaction is highly exothermic and one can expect film diffusion, then it doesn't make sense to have uniform distribution. It is good to have all your catalytic material on the outer surface of the catalyst particle. The same is desirable when one is dealing with series reactions, where a product intermediate is the desired product. When the amount of active metal to be incorporated in the support is very high, then it doesn't make sense to do impregnation. So one goes for compounding. where both the active phase and the support are co-precipitated simultaneously. A third area is coatings, like in automotive exhaust catalysts. In automotive exhaust catalysts, the flow rates are very high and the temperature of the exhaust gas is very high. So these catalysts are prone to film diffusion, diffusion limitations. Hence, it is important to load the active material as a micron thick uh, phase on a carrier such as a monolith or a honeycomb, which will not hinder the flow of gases. So you'll have very little pressure drop, and the substrate coated only on the channels of the monolith. So to do this, you need coating equipment, and it is very important to ensure that the substrate, this coatings are very uniform, and that the active phase, here again the distribution of the active phase along the length of this channel is important. So this calls for good equipment or appropriate equipment and proper process control. The opportunities in for a chemical engineer here are kinetics and modeling of competitive adsorption here, process control and equipment design such as for coatings. We then come to catalyst evaluation. Now the catalyst is ready and then it needs to be evaluated. This is similar to the slide we saw earlier when we do lab scale evaluation. This is a typical skid where you have means for pumping a liquid, means for feeding gas, furnace and a reactor with a furnace, and pressure safety valve, devices for measuring pressure, a heat exchanger for condensing, a gas liquid separator, and a product tank. So here you essentially screen catalyst formulations for conversion and selectivity. If one wants to do kinetic studies, then I won't reiterate again because we've already seen that in the earlier one. Use plug flow reaction conditions, study the intrinsic kinetics. One thing that is important in this is to determine or to have accelerated aging test protocols, because it is any end user or customer would want to know the life of the catalyst. So you develop accelerated aging test protocols. Like if your actual life is about say 2 years, then you should be able to predict the life of the catalyst through experiments which can be completed in maybe 2 to 4 months. So these are what are known as accelerated aging test protocols. And operating window, that is determining the effect of process parameters which give you the best performance, is also important. So principles of reaction engineering are applied in this. When it comes to kinetics of reaction, one can decide to go for a simple empirical model if one's objective is only to size the reactor. If one wants to understand if one wants to improve the catalyst, then one necessarily has to go for a mechanistic kind of model like a Huijsen-Watson or Langmuir-Hinchelwood-Huijsen-Watson models, in which you assume different steps such as adsorption of reactant on the catalyst is rate limiting, or surface reaction is rate limiting, or desorption of the product from the surface of the catalyst is rate limiting. And then you do model discrimination studies to determine the rate limiting step. So this allows one to understand which of these 3 steps is rate limiting and what changes to make in subsequent catalysts to improve them. Kinetics of deactivation is important. In order to do this, it is important to have knowledge of statistics to be able to do a statistical design of experiments. Sometimes statistical design of experiments can be very elaborate. Then one goes for composite designs. Composite designs are similar to are normally used when you want to do yield maximization, which is an area of study in process optimization, where you can also use surface response methods. Certain other things are in catalysis, you end up handling different kinds of solids, which could be a wet cake, or it could be a solid dry powder, or a formed catalyst shape. So solids handling and conveying are very important areas in which a chemical engineer can contribute. So this can be mechanical, such as belt conveyors, or even pneumatic or vacuum or one can even use pneumatic or vacuum conveyors. EHS, environment, health, safety, is another area which is important in catalysis, as is important in other areas as well. Hazards of exposure to fine powders, which may be pyrophoric, or hazardous chemicals, or spent catalyst, which could be pyrophoric and having coke, which can easily catch fire. Modeling and simulation are important. DEM, CFD, Aspen, which is a process design software, and density function theory are very useful in catalyst development design as well as application. Some new areas that have come up are 3D printing. In the equipment which I showed you in forming, it is not possible to. There's a limitation in the kind of shapes that one can make and in the kind of dies that one can make. But in 3D printing, one can make practically any shape that one can imagine. So that's the beauty of 3D printing. So this is an upcoming area, and people have also started investing heavily into this. Especially catalyst manufacturing companies have started investing heavily into this. Then there is what is known as atomic layer deposition, which facilitates tailoring the surface of a catalyst at the atomic scale. So this has a large implication on turnover rates, turnover frequencies, that is the activity of the catalyst, as well as product selectivity. Then you have high throughput screening, in which you have parallel reactors, very small reactors, which are parallel reactors, which come in sets of either 8 or 16. So one can study at least a minimum of 8 to 16 catalysts simultaneously with the same feedstock under the same conditions. So that speeds up testing of the catalyst. And then you have operando spectroscopy, where this technique enables one to do spectroscopic measurements when the catalyst is actually operating or carrying out doing the catalytic reaction. This was not possible in hitherto days. The key catalyst characteristics. So determining the characteristics of the catalyst are important for developing better catalysts and also from quality assurance point of view. Some properties are surface area, porosity, pore size distribution, topology, size and shape, bulk density, crush strength, accretion resistance, thermal resistance, the chemical composition of the catalyst, the spatial distribution of the active phase, some spectroscopic properties. And it is important to remember that many of these properties are interdependent. So it's a matter of optimization. For example, if I want to increase surface area, I have to be prepared to take a hit on porosity. Some tools that are used for these are design and modeling and simulation tools, such as Foresight, Compass, or Sorption for adsorption, CASTEP or DMOL3 for reactions, and Material Studio for different materials, as well as DEM and DFT. Well, that brings me to the last slide. And as you would have appreciated, catalysis is essentially collaboration. Thank you. If you have any questions, comments, or suggestions, I'd be happy to take them. Hello.
Okay, thank you, sir. Thank you so much for enlightening our students how to correlate the basic concept towards the engineering application, and that which was beautifully presented by you.
Thank you.
Thank you, sir. Yeah, I think till now I have not received any questions. So hope your presentation was very up to the mark, that the students have understood and enjoyed the session.
Yeah, you're welcome to email any queries that the participants may have. I'll be happy to answer them.
Okay, sir.
Yeah.
Sure, sir. Thank you, sir. So we can end the session here?
Oh, yeah. Thank you.
Okay. So you can stop sharing.
Yeah. Yeah,
okay.
Stop sharing.
Yes, sir. If there is any further questions from the student side, then I'll definitely forward it to you.
Sure.
And I'll share your details with the students also if they are having any questions.
Welcome. My pleasure.
Okay. Yeah. Thank you, sir. Have a good day.
You have a good day too. Thank you.
Yeah.
Thank you for the invite. Yeah.